Hello, I'm MC2 the worst rapper in the world. Oh, sorry, the second worst rapper in the world since Multi Tom Tom decided to start rapping. So, anyway, tonight we've got what I called a continuation of a discussion that FTFE started a couple weeks ago with the Mad Philosopher. How you doing there, Mad Philosopher?
I'm doing great. Sorry, I had my mic muted there for a moment.
All right. Well, good. Good to hear you. Good to have you. And I'm gonna call you James. That's what you said to call you. So, or Mad Phil, or whatever comes out. If I make any mistakes, don't worry about it. So, I did not prepare anything in particular because it was kind of a question and answer or just kind of an investigation type idea, right?
Yeah, honestly, I didn't either. I've got a lot of family stuff going on back home.
Okay.
So I tried to hastily gather some notes today, but
Okay.
guess we'll deal with what
Yeah. Well,
works.
I have stuff that I refer to, so I'm not unprepared. I had a guy a couple weeks ago who I told him I was unprepared, and then I had no notes, and he's like, "Well, how come you have all this stuff?" I'm like, "Well, I have things, I guess." So, anyway, my notes, my folder of whatever stuff I look at. So how did you? I guess that we can start with that. How did you get to where you are today? In
Oh,
thinking about the Earth.
well, I guess I've always been a little bit conspiratorial, uh, in one way or another. Um, as early as the 9/11, the day that happened. Yeah, I know. I'm not trying to get into all that. Sorry, but that sort of opened my eyes a little bit and made me look a little deeper because it piqued my interest. Uh, and then I started looking into the moon landings, and I guess from there it was, if the moon landings didn't happen, right? If there was something fishy going on there, it made me wonder if we've even been to space. Like if we haven't been on the moon, then did we even go to space? And if we haven't gone to space, well, is space even real? Right. So I started having to backtrack a little bit and start to re-examine what I was taught, which honestly is rather exciting. I just shouldn't. I would never support anyone just believing everything they were taught in school and just that be it for the rest of their life.
Yep.
Um, I think that's a little I
Okay.
don't know.
Did you
I don't know how to
what was
say
there
it.
like something you came across or a video or something?
Oh,
I
about
mean,
the flat Earth, right?
yeah,
Right.
yeah.
Okay. Yeah, in 2015, about summer, um, I had heard about it. So, I think I saw a video, or like the title of a video come across my YouTube scouring, and I didn't give it any, I didn't pay it any mind. Um, I didn't. I thought it was dumb. I thought it was like a test to see how dumb the human race has gotten.
I thought a lot of people think that. Yeah.
Because a lot of memes came out in the those years. So I just thought it was another meme. After seeing a few more videos came out, I started to look. All right, let me at least give it a go. So give the old college try or something, however the term is. Um, so I saw this video saying that gravity is fake. This guy did this little thing with the slinky. He let it go, and the bottom stayed still, just suspended in air, while the top came to it, and then the top pushed it the rest of the way down. I thought that was interesting, and then did the um, he dropped his keys in one hand, he let the balloon go in the other, the helium balloon, and it went up, and he was saying, why aren't they just the equal and opposite reactions of each other? My baby is crying, so I'm gonna try to wrap this up real quick and then
Okay.
take a quick pause. Um, so I started looking at it, thinking, okay, why shouldn't the Earth be a ball? And then started uncovering little interesting bits, but like that equal and opposite reaction with the density and buoyancy. The keys falling because they're denser, helium balloon rising because it's less dense. Um, Stuff like that. And I'm sorry, this is getting a little distracting. I'll be right back.
Yeah, go ahead. So, all right, well, he's away for a minute here, but does it sound any different than anybody else? So far, it sounds pretty similar to me. Happened on some videos and didn't quite have the physics background, so I don't know. Maybe we can cover some physics and understand it. So, but he's away right now. He doesn't hear me. So, let me say later tonight in just under 2 hours, I have another discussion with a guy called Keith. I don't know how to say his last name. Keith. It starts with a K. And he's thinks 5G and radio frequency is harmful and causes a certain popular virus these days. Has evidence, he says, substantial evidence. And if you've not seen the thumbnail, he actually does walk around with a tinfoil hat on, for real. He also has like things he wears in his clothes. So, and he sent pictures. We're gonna cover it. So, that's gonna be pretty interesting, I think. He's a nice guy. I've been chatting with him back and forth on Facebook Messenger all day. So, that's going to be cool. Cool. So, all right. Hey, did you, how did you make the baby stop crying? Lots of Benadryl? I hope not.
No, no. I just he was laying back in his chair that he couldn't really crawl out of. So I just let him put him down on the floor and let him play with his little toys.
Okay. Well, good. Okay. So, a couple things. Maybe we could. I could just explain something quick about buoyancy. Actually, buoyancy.
Yeah, sure. Go ahead.
Yeah, buoyancy is a result of gravity. The reason why is the air that's around here, right, is more dense than helium. When they put the helium in the balloon, it fills that certain volume of the balloon. And there's not as much material, atoms, inside the balloon. So the air around the balloon says, hey, I want to go down more than you want to go down, contents of balloon. So what we're going to do is we're going to shove you out. We get to be down here and you got to go up. But in a vacuum, if you get a balloon in a vacuum chamber, and some people have done this. I think Cody's lab did it. He has a little vacuum chamber. It's hard to get because balloons expand in the vacuum too, so you kind of need the Mylar balloons that don't expand. But the balloons actually then fall. So helium balloon falls in a vacuum, so or in a near vacuum. So it's just, I think it's probably just a misunderstanding of physics. And when people present it in these videos, they intentionally rely on people's misunderstanding of physics to kind of trick them. I think it's a little dishonest. So
that balloon in a vacuum, what was that showing exactly?
What do you mean? Well, so he put a balloon in a vacuum chamber. He had it. It was at the top, right? Because it was floating. And then as he pulled out the air, the balloon got bigger, but it fell as it once the vacuum got strong enough.
Well, I guess what I'm asking was, are you saying that it was still falling because of gravity?
Yeah.
Or
yeah.
Like what? Okay. Is there a way to prove that gravity is the force that was pulling that down, even in a vacuum?
Well, first of all,
Earth, right?
Another misconception is that science doesn't prove things. That's the reality is science doesn't
Well,
prove
okay,
things.
okay,
So people think.
demonstrate, right? No,
So
I
yeah.
get you.
So just to be sure we have the foundation. Science finds evidence for things, and when there's a lot of evidence for things, then we have a lot of understanding of it, and we're very confident that our understanding is correct. But science
Right.
is always open to say, hey, there may be something we're missing. So if somebody has something else, bring it up and, disprove the current understanding of it. There's an open invitation and there's of course resistance. People are like, yeah, I don't think that makes sense, but it happens. People have, kind of changed ideas about stuff in the past. So how do we know that gravity is pulling it down, that mass attracting mass is pulling it down? We do know the formula. Do you know the formula for gravity?
Uh, which gravity? Newtonian gravity or Einsteinian gravity with general relativity?
Well, the formula for Einsteinian gravity, you can do it. It starts with Einstein's field equations. You can simplify them down specifically for gravity, and what happens is you wind up with the exact same formula with one additional thing. The Lorentz contraction is multiplied by the whole thing. So I'll tell the Newtonian formula is F equals g, the gravitational constant, times the mass of one object times the mass of the other object divided by the radius squared. To bring in Einsteinian gravity, you just multiply all of that by the Lorentz factor, which is based on their relative speed. And if the relative speed is not anywhere close to the speed of gravity, the speed of light, then that value is so close to 1 that it's buried way deep in any margin of error. So it's negligible, and you can leave it out of the equation, except when the speed is high enough, a large enough percentage of the speed of light. So they're the same equation unless you're moving really fast.
How do you reconcile that equation without radius?
With what do you mean?
Radius is part of the equation, right?
Sure.
How did you get the radius?
Oh, people have measured the radius. I measured the radius last week.
How do you measure? Go ahead. How do you measure the radius?
So, I'm sure you've heard of Eratosthenes. Now, he did one measurement. So, and one measurement doesn't tell you the shape of the Earth, right? So, but it does tell you, if you know the shape of the Earth to be a sphere, then that tells you accurately the radius. If you have more than one measurement of on the same day or at the same time of the Eratosthenes style experiment, then you can narrow down whether or not it's flat or spherical. So you start with your hypothesis. You say, let's assume for our hypothesis the Earth is flat, and we'll take 2 or 3 or 4 different measurements of the angle to the sun on the same day, knowing where the sun's subsolar point is on that day. So it's easy to do on the days of the equinox or the solstice because we know where the sun is on those days, right? On the December solstice, it's over the Tropic of Capricorn. And so if you know your latitude, then you can get your latitude and just do simple math to go from your latitude to the Tropic of Capricorn, multiply by the number of miles per degree latitude, which is 69 miles, 110 kilometers, or 60 nautical miles. So you know your distance to the Tropic of Capricorn. There's no question about this. The actual definition of 60 nautical miles is 1 degree of latitude. So we know where that is. We know how far away we are. Then you can just do simple triangulation once you know the angle. Right? So you know the angle to where the sun is. You know how far it is across the plane, assuming a flat Earth, and then you know the 90 degrees here, right? So you got angle, side, angle. You can solve the triangle, so it tells you how high the sun is, right? So if you do that with one measurement, then it works for flat Earth. But as soon as you do 2 measurements, then they need to coincide, right? So if I'm at 45 degrees north, and a friend of mine's at 31 degrees north. We both measured it, right? And he's in there, Round Thinker, he's in there, in the chat right now. And we both measured it on the same day and got different numbers for the elevation of the sun, assuming a flat Earth. Okay? So, I don't know, triangulation is done in 8th grade, and most people don't use it very often, so kind of forget about how to do it. The nice thing is, if you just Google triangle calculator, you can find a triangle calculator. You plug in the angle, the side, the angle, and it'll tell you everything about it. So anybody can do it. It's not that difficult. You don't actually have to do the trigonometry by hand, but you can. And typically you're going to use an arctangent there for that, or tangent for that, and then go. So anyway. The point is, it didn't work if it was flat. So then we had the hypothesis, what if the Earth is a sphere and the sun is very far away? What is the radius? And each of us then get a radius based on our latitude and the angle to the sun, right? And it tells us the radius. Each one of us, and there were, I think, 4 that did it in December. And Round Thinker, how many did we have? Did we have 3 or 4 just last week? That also measured the radius. And both times, all of the measurements wound up to be the same radius within a very small margin of error. So there you go. That's how we know the radius ourselves. There's other ways that are much more accurate, because measuring the angle to the sun is, our margin of error is within, 1 degree in the sky, which works out to be bigger margin of error than you can do if you have some more precise measurements instruments, right?
Eratosthenes, where do you know where he was measuring?
I don't know. We aren't Eratosthenes. We did our own measurements. We did our own math. So I don't really care where he was. It's just his technique. Right.
Okay. I would love to go into more detail on that, maybe off screen a little bit when there's a little less pressure.
Okay. So I have on my website, and I'll send you the link. I have on my website the actual measurements that we did in December, and I actually just this week I was a little late in sending my stuff to Round Thinker, and so I just sent him back some information by email today so that he can do the rest of the math. So
I would love to be a part of some of these.
Sure.
Because if I'm gonna be intellectually honest, right, I would love to I would love to believe you, but if I'm gonna be intellectually honest, I have to be part of that to make sure that I can measure that for myself and know that it's what I'm measuring is a ball and not just maybe like the radius of or maybe like a circumference of a flat disc, maybe not a flat disc, maybe a distance of the disc, like from north to however far out.
Yeah. So here's the cool thing. We don't have to wait for a solstice because we know where the subsolar point is of the sun at any time. That's pretty well-known information. So we could do it any time. And what you need, though, is you need somebody you trust that's at a different latitude than you, right? So you're at, I don't know where you are, right? You're somewhere east of where I am in Minnesota. You're going to be, I'm guessing, south of the 45th latitude where I am. But you want somebody that's
honestly,
different.
I haven't checked.
Yeah, but it doesn't matter in particular. So then what you want is you want to find somebody that's as far away from your latitude as possible to do the same thing on ideally the same day, right? So you both need sunny weather. I did it. I was not able to do it in March because it was cloudy that day. But like I said, it doesn't have to be on that particular day. It's just kind of fun to do it that day because everybody can kind of point to that day that they did it, So, here. Round Thinker has his spreadsheet. is this the one from? I'll pull it up here. Oh, he has all three of them. Winter solstice, spring equinox, summer solstice. Of course, these are northern hemisphere centric. So there it is. Oh, that's just for his spot in Israel. So there you go.
Okay, I see it in the YouTube chat.
Yep. So there's his results for his position. And of course, his latitude did not change. So there you go. Yeah, I'll send you a little more information, and yeah, if you want, I can do it any day it's sunny here and send you what I have. So.
All right. Another concern for the globe that I had, and I've got a video reference for this, is the core. How it I don't know how a molten metal or superheated metal, solid metal core could create a magnetic field. There's a here. I'll send you a video for. Oh wait, no, that's not the right one. Anyways, it's there was a dynamo, not experiment. I guess they created this thing, spinning molten. Here, this.
He's sending it in the Zoom chat or in the
the Zoom chat.
Okay, hold on.
Okay, so this guy, these people, they created a huge spinning sphere of molten sodium to try to replicate the outer core, the molten outer core, because they were talking about the inner core being solid, the nickel and iron, but being ferromagnetic and that they were at such high temperatures, you couldn't really get anything from that. You can't create anything from that. So the same with the outer mantle. The mantle wouldn't sustain or create or sustain a magnetic field either. So what you're left with is the molten outer core, which is supposed to be revolving at however fast. And what they're trying to do is replicate the outer core, creating a magnetic field. But what they also say in this very video, around 4 minutes and 40 some odd seconds, between there and 450, he admits that you don't really care where the tickle comes from, because they need to introduce some sort of electric current. He says it doesn't have to be much; it's infinitesimal, little, almost nothing, but it has to be introduced. And the guy who was interviewing the person who works there was asking, how do you do that? If how does that happen in nature? You don't really see that in nature. Where's the current come from? And the guy says, well, you don't really care where the current comes from. Well, for me, I kind of do care. I want to know how this magnetic field is created, how the core is supposed to be, what creates it, and how the core is even supposed to exist.
So, all right, I have here, which I'll paste into the chat here. They've done it. Here's an experiment that they did it in 1999. Magnetic field saturation in the Riga dynamo experiment. So I'll give that to you. You can read it on your own time. We're not going to go into it now, but there is they did create a dynamo effect with and magnetism. Let's see. I think it was nickel, not sodium. So the problem is, of course, what is the alternative flat Earth explanation for it? Because so far we have a pretty good explanation for it, because the dynamos have been created, and all of these things are not just hypothetical; they're actually been confirmed. But what is the flat Earth explanation for the magnetic field of the Earth? Because it moves, and it's inconsistent. It's not just a north-south at one point and another, right? It moves, and it's got different strengths all over the Earth.
I would love to know what creates the torus field around the Earth. Unfortunately, I don't have all those answers.
Okay, so it's not actually a torus field, because the south magnetic pole isn't all directions out, right? And I've seen over and over again flat Earth videos that have this.
There's more than one torus field. There's a single pole torus field, and there's a hyperboloid torus field with two separate poles. So you have a torus field, or the North Pole at top, South Pole on the bottom, and then there's this flat plane of inertia in the middle.
Yeah. So here's my point, though. The magnetic field of the Earth, the North Pole is near. Sorry, the North Magnetic Pole is near the North Geographic Pole, and it's been moving closer. It used to be down close to Resolute, Canada, which was actually pretty far south, and now it's moved quite a bit north. The South Magnetic Pole is in the water between Australia and Antarctica. So the flat Earth ideas that I've seen, people take a magnet and they put it in the middle, right? And then they just put like a piece of paper on top of it with the AE map on it, and they say, well, everywhere this direction is south, completely missing the actual measured location of the South Magnetic Pole is not the actual South Pole. It's in the water south of Australia. So they completely mismatch reality there. The other problem then they have is that none of the other observations about the magnetic pole match. It's not just the location, right? So I can just put a magnet and imagine like a horseshoe magnet on the North and South Pole. No explanation for why it moves. Number two is that the declination doesn't work. So you know what magnetic declination is?
Why don't you go ahead and tell me?
Okay.
I probably do.
You probably do. I think most people kind of know this. Magnetic north isn't true north everywhere. In fact, most of the world, it's not true north, and it's far enough off in lots of places that maps have to be updated if you're going to use it for navigation. And if you're using an old map, it's against the law to fly with a map that's out of date by a certain amount. The FAA has regulations on that, so maybe not against the law. I don't know, but you can't fly with an old map because the declination moves and it's wrong. So like I think in Florida, the declination is about 10 degrees to the east. On the southern edge of California, it's about 19 degrees to the other side. The zero declination line goes through Minnesota, not far from where I live, real close to the Mall of America. So the declination, though, here's the deal. If you were to put just two poles, north and south, none of it matches with the actual measured declination. For example, South Africa, the declination is way, way off of true north. But if you just put the two poles there and say, well, this is where the magnetic flux lines would be, it doesn't match. The second thing that's very, very far off is the inclination, which is the actual vertical amount of the field. Things like in New Zealand, it's totally wrong using the flat Earth, even the two poles. And then the third would be the field strength. The lowest magnetic field strength of the Earth's magnetic field is in Brazil and Paraguay, Uruguay, right in that area. And then as you go farther south, it gets larger again. It increases, except that is going away from where you would expect it to. So the field strength doesn't match at all either. So those three things, none of them matches any explanation for flat Earth at all.
I've heard people talk about this before. How exactly is that? Were those measured, like especially down in the southern hemisphere?
There's stations all over the world, and then people go. So they have permanent stations, and they're scattered around everywhere that people, that have land. So there's some down in the southern points of South America, all over Australia, New Zealand, Africa. And so then they'll go out to different areas and they'll get more updated measurements for certain areas if they need. What's the method?
What's the method of measurement? How do they measure? Like, cause when I asked that, you said there's stations.
Oh,
well, okay. How do the stations measure?
Yeah,
how do they get their data?
I don't know the specifics of it, but these are, and we can certainly look at it, but these are people that this is their career. They are full-time people that measure the Earth's magnetic field strength and position and angles and all that. So there are nowadays, you can actually just buy three-dimensional magnetic silicon-based tools, and they're digital, so you can hook it up to your Arduino or Raspberry Pi and write your own software if you want. Or you can buy there's instruments that measure the field strength and direction in 3 dimensions. So that's not they aren't actually that expensive either. You can use your own to a certain extent. You can use a nice, hold on, let me get my I have a compass somewhere here. I got my magnetic ball. I don't know. Darn it. Well, I don't. Anyway, a compass. There's compasses that are for northern hemisphere and southern hemisphere because of the inclination. They have a weight on one side because the field strength tips it, right? So as you go farther north, it tips it farther and farther. And when you're above the magnetic North Pole, it's vertical, right? It's 90 degrees. And when you're above the magnetic South Pole, it's negative 90. They just assign south down being negative 90 and north up, or north down being positive 90. So you can use then a good world compass, right? So some compasses then have a bigger gimbal inside and a larger capsule so that they can tip. And so what you can do is you can actually take them and turn them on their side, and then you can measure the angle of the inclination. They do make a magnetic inclinometer that I thought about buying, but it's $50. That's designed for doing that. And so you can get both the declination and the inclination pretty easily. To actually get the field strength, you need a more precise instrument.
Do you know of a database maybe, or some sort of collective get together of flat earthers and globe earthers that can put all of these tools together and everyone do experiments with all of these tools to measure literally absolutely everything, and literally create a new model that is experimented, tested, mathed the shit out of, to get an independent model of the Earth, instead of just believing like NASA or governments. Why not independent researchers create a model, and if it matches with everything that everyone else says, fantastic, fabulous. All right, the Earth is a globe.
Well, a lot of people have done things like that, and then flat earthers just reject the data. So it's what happens. So
I'd like a little more honest and I don't know, a little more honest middle ground where there's not such.
So so you can order yourself a good compass and a inclinometer right there for yourself, and then you can compare that to the world geomagnetic model to see if it matches for your location. And you could, I guess, send that to some friends at different locations and see if it matches. Here's what you'll find: they match. Nobody's ever found those things that don't match. It's not really. I mean,
I wasn't just talking about that. I was talking about literally everything.
Well, what else is there, right? So
what do you mean? What else is there? I'm talking about the Earth, man.
Well, I measured the radius, and I had a hypothesis of the Earth being flat, and it didn't work out. So flat Earth disproven. Did that already, I guess.
But that's a mathematical calculation, though.
So science uses math. That's fine.
Well, yeah, but it also uses observations and testable results, testable experiments, stuff, something that's tangible, not something that you just jot down on paper and Earth is a globe.
Well, science doesn't limit itself to what you just limited it to. So, right? There's lots of ways to measure things, not just I have to touch it. Right?
I didn't just try to limit it to that. That was just an example.
Yeah. Let's see. Let me look. I have some notes here. So, the thing about gravity. So you talked about you didn't think gravity is real. That there is a downward acceleration of about 9.1 meters per second squared, all over the Earth. Right. What is?
Yeah, that's an observation.
Yeah. So what is the cause of that? If it's not mass attracting mass.
Well, general relativity doesn't even say mass attracts mass. Well, I mean, in the way that what you just described sounds very Newtonian.
Yes, because we live in a Newtonian world, and I am a Newtonian girl.
Okay. Have you looked into the electric universe at all?
I have. It doesn't make any sense.
It doesn't? Why not? Like, what aspects of it doesn't make sense?
It doesn't explain the downward acceleration in the least. It doesn't even come close.
Well, there is an explanation. Not sure how to prove it per se. But they mentioned dielectric acceleration and dielectric avoidance, where dielectric avoidance would be the direction, dielectric acceleration would be the attraction.
Okay, and so do we have formulas for that so we can test it? I'll write it down so we can, because if it doesn't come out 9.81 meters per second squared, then, then it doesn't get off the ground, An
observation of acceleration isn't a measurement of force, though.
I don't need to play semantics games. I mean, there's a 9.8 meters per second squared accelerating force down all over the Earth. So what's the cause of that? And if you don't have an answer for it, and there is already an answer for it, then it's really difficult to be honest and not accept the answer that's been provided, right?
Well, that's just, I don't have to accept an explanation just because there's an explanation for it.
Sure, but it's a little intellectually dishonest to reject it for no reason.
No, not for no reason. Just because it hasn't been demonstrated. Just because there's an explanation. Oh, it's gravity. That's why. You haven't tested the cause. The cause hasn't been found. Just because it falls and you call it gravity. Okay, well, what's causing the force to exist?
Okay, so if you're going to get nitpicky and semantic on the cause, then you need to replace it with the cause that you have. Right? Don't try to replace it with nothing.
I freely admitted.
So if you don't have a cause, then that's not science. That's just science denialism, right? And And that's
that's
kind of at the
that's
core. The real core of flat Earth is science denialism. Taking the stuff
not
that
at
people
all.
have done and say, nah, I don't like that for not any really good reason. And I'm going to substitute this other thing that doesn't really work, but I'm still going to go with it. So
That's not at all what we're
so
doing.
is there, for example, to disprove gravity, then you would need to find some places where it doesn't work, for example. Do you have any examples where gravity doesn't work?
An example where gravity doesn't work. Well, I would need an example of how gravity works first.
Well, it's F
Like
equals G times M1 times M2 or divided by the radius squared.
But see, that assumes the radius again.
Well, no, we measured the radius, so we're done with that. We have a known radius of the spherical Earth.
You can't ever be done with anything in science. You admitted that earlier.
Of course, yeah. So we have a radius, and our margin of error is very small on that. So we're not assuming the radius. We know the radius. We measured it.
How do you know it's a sphere that you're measuring?
How do I know?
How do you know it's not a radius? How do you know it's not a radius of a circle? Why is it a sphere?
Well, the three-dimensional shape is of a sphere is the only shape on which that works.
How?
How what?
What you just said. I'm asking you to
okay. So the measurements that Round Thinker and I did, those only work on a sphere to come out because we're not in the same area, right? So you could draw out. You could try a couple different geometry attempts, and you could maybe say, well, it would work on a flat surfaced thing like a dodecahedron or a icosahedron or something like that. But that would be a little more of a stretch. But it certainly could, based on just our measurements in isolations. But then there's other measurements, of course. The angle to the north celestial pole and south celestial pole only works on the surface of a sphere. It does not work on any other surface.
So the what's for the north and south celestial pole?
The declination. So as you travel north and south, the angle from true level up to the north celestial pole or south celestial pole only works on a sphere.
Why does it only work on a sphere? Why can't the sky be different on a flat Earth?
Well,
because of how far you are?
Can you produce a shape that would work for?
What do you mean a shape? It's a phenomenon, not a shape.
No. What shape might
you're looking at? You're looking at the sky.
Of course, yeah.
How are you looking at the sky and deducing the shape beneath your feet?
Easy by triangulation. It's a great question, and it's a really easy way to do it. So I'll show you here a thing. Assuming a flat Earth.
I think you're.
Right? And I'm gonna do a angle here. Now I'm in Minnesota. I'm gonna approximate 45 degrees.
I went over this with FTFE when I was with him. You put a picture in the center of your ceiling, walk from one corner of your room to the other. It's going to look different.
All right, so here we go. I'm just showing you the triangulation.
Angle,
right? So there's the north celestial pole at 45 degrees. Now I know how far I am from the north celestial pole because we know how many miles there are between each line of latitude, right? I'm 45 degrees from the North Pole, right? 4569 times 3,105 miles. Okay, that's how many miles away I am from the North Pole, right? Now, this is a 45, 45, 90 triangle. That tells us that this angle here, this side is also the same. So it's 3105. Okay, so now we've measured, this is easy to do, anybody can confirm it. We've measured the elevation of the North Celestial Pole as is apparent from Minneapolis, Minnesota, right? Or anywhere that's 45 degrees north latitude. Now the problem is if you go to 30 degrees north latitude, right? Now, what's the elevation of the sun, or sorry, what's the elevation of the North Celestial Pole at 30 degrees north latitude?
What? Sorry, say that again.
What's the elevation of the North Celestial Pole from 30 degrees north latitude?
I don't know. What you tell me?
30. That's actually how the lines of latitude were put together, right? It's the elevation to the North Celestial Pole or South Celestial Pole tells us your latitude. So the problem is, assuming a flat Earth, right? So here's this new measurement here, 30 degrees, and that same 3105 elevation. We got to keep that, right? Because we already measured that. Now 30 degrees north latitude is how far from the North Pole?
Go on, I'm listening.
Well, it's 60 degrees latitude from the North Pole, so you just multiply 60 by 69, 4,140. Oh, there's a sloppy line. 4,140. All right, so here's 4,140, right? So that's how far it is. Now we can test now to see if it matches, right? Now, this is stuff that anybody can do any day of the year if they can see the stars, see the sky at night, right? So I'm gonna bring up an actual triangle calculator. Right triangle calculator. So we've got A is angle side, all right, 30 degrees for the one angle, right? And we've got a right angle there, and then we know that the length of the one is 4140. There we go. So now I'll write this down here. A elevation 2390. Okay, so what I did is solve that. This is just simple math, right? So we've got, again, the distance from 30 degrees north latitude to the North Pole is 4140 miles, right? The angle is 30 degrees, easy to calculate. This elevation here, if the Earth is flat, from the 30 degrees north latitude is 2390 miles. Same day, same time, every day of the year, from 45 degrees north, the elevation of the North Celestial Pole is 3105. Every day of the year, it's 2390 from 30 degrees north. What you'll find is that from every single position along every latitude, it doesn't match. This is calculating perspective. We use triangulation to calculate perspective. So that doesn't work. I just falsified flat Earth again. But if we put it on a sphere, let me see, I got a circle right here. My old Echo. And we'll put, I kind of messed it up there. I should use my ruler. That's a good idea. North Celestial Pole from the North Pole. I drew the Earth sideways just for fun. Right there. All right. North Pole, it's straight up. From 45 degrees north, it's 45 degrees. right? And from 30 degrees, it's 30 degrees. So every position, every line of latitude it works on a sphere. Now, that would not work on a dodecahedron or an icosahedron or any other shape that's got flat faces but, kind of ridges. So that's how we know it's a sphere.
If I could get to Polaris, I would love to corroborate what you said.
But you don't need to go to places to triangulate their position. The entire field of surveying is based on measuring angles and then knowing the distance between them by using triangulation. So we don't need to go to some place with a tape measure in order to know how far away it is.
So I think I don't know why I need to explain the difference of surveying the ground. They're surveying the ground is much different than surveying the sky.
So are you just trying? Wait, you said you weren't into denialism. That's denialism if you're just going to try to throw away, a mechanism of finding out the shape of the thing we live on just because you don't like it.
No,
right?
I didn't say that.
Okay, so
No.
There's nothing wrong unless you can find something wrong with my method. There's nothing wrong that I know of that with using observations in the sky to find out the shape of the thing we live on.
Because you can't actually get to anything that you're looking at in the sky. You're assuming the distance is.
I didn't assume any distance.
You just said that the distance. You know the distance to Polaris
On flat Earth.
Yeah.
Just on flat Earth. We can try, if the Earth is flat, we can triangulate the elevation of the North Celestial Pole from any position.
Right? Yeah, assuming that how did you do that though?
And
because you can see it doesn't mean that it's exactly where you think you're looking at.
Oh well, please present your evidence.
I would, if I could go there, I would.
No. You said just because you can see it doesn't mean you can measure. Present your evidence supporting that claim.
What are you talking about? You guys try to use what was it, parallax all the time? If you know
just no. The topic is triangulation. You're trying to tell me that triangulation doesn't work. Present your evidence.
I didn't say that. I didn't say. Oh my! I think you're misconstruing what I'm saying.
What you're trying to say that we cannot use triangulation of the North Celestial Pole on a flat Earth to see how high the North Celestial Pole is on the flat Earth.
Because you can't go there and verify that your math is correct.
No, but we don't need to go there to verify
Why
the math
not?
Is correct. Because we can use triangulation. So
you can use math to verify math instead of
we can use math.
Experimentation.
We can use math and measurements to measure things.
Measurements. You're using observations.
Yeah, the measurement would be the angle.
Measurement would be the distance. Would be the distance between you and the North Pole. That you're still not measuring anything in the sky. You're looking in the sky and hoping that your math is correct.
Well, if the math is wrong, please tell me.
Math.
Is the math wrong?
I would love to. If I can get there, I would tell you.
You don't have to go there to verify that my math is correct or not.
You really do, though. You need to go to.
Well, then present the evidence that you must go somewhere in order to know the distance to it, and there's no other way to know the distance to something. You need to now disprove that triangulation works. Go ahead.
No. That's not.
That's what you're trying to do. You're trying to disprove triangulation.
No,
Go ahead.
I'm not. No, because triangulation on the ground works for the ground. You're assuming that it works the same for the sky. You need to present evidence that it works the same for the sky.
No, I'm sorry. Triangulation works for everything, everywhere, always. Unless you have an
that's
exception.
A claim.
So
friend, is the claim.
The entire field of surveying is based on that axiom. So yeah, it's an axiom for which nobody has ever presented anything to the contrary.
You're talking about on the ground, though. I'm not disputing results on the ground. You're assuming that what the methods for calculating the ground also works for the sky.
Hmm.
That, my friend, is the claim that I'm trying to that I have trouble accepting, because
Okay.
that is a claim that I need
So,
evidence for.
all right. So then, do you have any measurements of the flatness of the Earth?
How many laser tests have been done?
Please present. Now, hold on. Let me make it clear. A measurement has units and a margin of error analysis. Present.
Mm-hmm.
Go ahead.
Such as beam divergent, right? I mean, that could be calculated in margin of error, right?
Beam divergence. Sure.
Beam divergence.
Yeah. The diameter of the cone of the laser as it strikes the target.
Okay, well then let me get the FE core real quick. And I'll even get videos of other laser tests.
Let's start with one. I hope there's units and margin of error analysis.
Here, I'll even open it up and go over it with you.
All right, I will. You can present. So in Zoom, you should be able to present. You can pick your window. Yeah, pick a window. Don't do like a whole screen, because then that shows a little too much information, I think.
How do I do that?
So
I do that on here.
On the screen there. Let's see, where is it? On the bottom center, there's a thing that says share screen. Do you have that?
Share screen. Okay. Oh, right. Gotcha. One quick sec. This one. Share. There, can you see that?
Let me see. Yes.
Okay. Let me. All right. Where 121 pages? Where am I supposed? Hungarian measurement. 21st of. Fraction conditions, measurements. I don't know how to present this as my presentation, since I wasn't the one. I wasn't part of this. I mean, I can. Of course, I'm gonna try to wing it.
Yeah. Well, let's do
really
this. Let's. I can address it. Jump to measurement 6. Because they do 7 measurements. 5, 6, and 7 have some good details on them. There's 4, almost there.
Measurement 6. All right.
Okay. So now keep going a little farther. Let's see. There's a temperature reading where they show 2 meters above the ground and right at the water level, the temperature readings.
Right here, temperature and humidity.
Yep. So you see at sea level, or the water level, 9.6 degrees Celsius. Right? And then at 2 meters, 11.6 degrees Celsius.
Okay.
Right? So let's just keep that in mind there, that little difference in temperature. So, all right, keep going. What was it that you were showing?
At 2, the measurements of how, hold on. Measurements through, it shows no curve drop, no drop in elevation.
Well, where?
Over how.
Where does it say that? How high was the beam when it struck the other side there on for like measurement number 6? How high did it hit the target?
Let's get to the actual. Target.
Yeah, they didn't. They didn't hit a target. So there, you're done with 6. You're up to 7. 7 has the same results as 6. It didn't hit a target. They didn't actually have it hit a target. They pointed on the early ones, the real short ones they did. But 5, 6, and 7, they did not have it hit a target. They could not get it to hit a target and have just a dot on the target to find out the elevation of that dot. What they did is they pointed their camera towards the other side, and they saw the light, but they don't know how big the cone was. That's problem number 1. Problem number 2 is the measurements of temperature. 9.6 degrees at sea level, 11.6 degrees 2 meters above sea level. So when calculating the effects of refraction, and the guy who did this, who claims to be some sort of a PhD in a light type field, didn't know to calculate lapse rate, and he did not calculate the lapse rate. That's a lapse rate of 1 degree per meter Celsius. That's a very, very strong lapse rate. All you need is a lapse rate of 1 degree per 9 meters in order to have the light curve at the same radius as the radius of the Earth. And they have, just in this one particular measurement, a much stronger lapse rate than that. So what they actually did in the FE Core Lake Balaton test is they confirmed the sphericity of the Earth because they measured the temperature. This is the only flat Earth measurement that I've ever seen where they measured the temperature. And it's kind of embarrassing for them because they measured it and it shows that the light will bend due to refraction. So if you don't understand refraction, you can look at my webpage, mctoon.net/refraction, and there's a whole bunch of studies about the effects of refraction in the atmosphere. So thank you for bringing that up. It's excellent globe evidence.
What can you go over that the
Yes.
You just said
yeah.
Again,
so
the lapse or something.
Lapse
what was
rate.
it?
Yeah. So lapse rate is
lapse
the
rate
change in temperature with elevation. That's the lapse rate.
Okay.
And it's measured in degrees per meter. Right.
Okay.
A lapse rate of 0.1 to 0.09, which is somewhere in the range of 1 degree Celsius per 9 meters. Right in that range there, the lapse rate. That lapse rate will curve light at the same radius. So the ray of light is curved as it passes through that medium. It curves at the same radius as the radius of the Earth at that lapse rate of 0.1. Right? They measured a lapse rate of 1.0, which is a much stronger curve. Now, they didn't measure at 1 meter or at 3 meters or 5 or 10 meters, right? So we don't know outside that range. But we do know that there's a very strong lapse rate, very high lapse rate. And so then you can calculate what's called the coefficient of refraction from that. A coefficient of refraction of 1.0 is like I said, corresponds to a lapse rate of about 0.1, which is the radius of the Earth is the same as the radius of the curve of the arc of light. So you can.
Can you post something for me to?
Yes, yeah. I can. I'll put that in the live chat here. This is from Andrew Young. That's not quite the right one. Let me get the right one here. So Andrew Young is a PhD doctor at San Diego State University. Has done a lot with refraction. He's one of the top experts in the world in that field. So let's see. I want to get the right one. There's a couple different. He's got a lot of information, a ton of information, really good stuff. So let's see. Is this the one? There it is. All right. That's the one. Atmospheric refraction. And let me send it to you here. So yeah, and I love the FE Core one. It's kind of an ambush. Sorry, I let you just walk into it. They totally measured the curve of the Earth. Not measured, confirmed. So there, I sent it to you there.
Yeah,
so,
I'm looking at it.
Yeah. So why don't you look at that later? Do you have any other evidence, any other measurements, since that one confirms the Earth being spherical?
I was really just trying to have a discussion, not an actual formal debate.
Yeah. Well. Yeah. Do you? Yeah. But so what? What other things do you think point to the Earth being flat?
Gas pressure. I don't know. I don't see how gravity can keep gas pressure in, or how gravity can be the cause. And if it's not gravity, then please tell me how we can have gas pressure without the molecules fucking off to space, as some of my guys say.
Yeah, you think that space sucks off the Earth?
Well, I mean,
all right. So yeah. So first of all, a pressure of 0 doesn't exist. There is no pure vacuum. So there is a relative vacuum. So you buy a bottle of Snapple, that little top is down, and you open it, and that top pops up. The inside of it is under vacuum. It's not 0. It's just less than the atmospheric pressure.
Right.
So that is what we measure. And if you've looked at like Dwayne Kellum, a flat earther who sends up cameras in balloons, he also has barometers on there, and it measures the drop in pressure with increasing elevation. So people have sent up in the 50s. They sent up rockets to specifically measure pressure, atmospheric pressure. They got up to 220 kilometers with these rockets. And they cataloged all of it, and then through different experiments in this 1960, 62, I think, and then in 1976 they updated this, and it's called U.S. Standard Atmosphere, which is the different pressures, measured pressures, and then formulas to use in instruments to know your elevation based on pressure, right? So airplanes know their elevation based on pressure. They use the specific equations in this U.S. Standard Atmosphere document, which is based on measurements for the decreasing pressure with increasing elevation. Now, we know that there is a downward accelerating force, right? You throw something up, it goes to the top, and then it comes back down, right? Air molecules are no different than a pen or a bowling ball, right? everything is pulled down. Whether it's mass attracting mass or something else, there is a downward accelerating force. So whatever is causing that is what's pulling it down. So as you go higher, there is less and less pressure because there isn't as much above it, right? So down here at the surface, we have the entire stack of atmosphere above us, and as we go up farther, we have less. So that's why we have a decreasing pressure. As you get higher, it just decreases more and more, and it never gets to zero. So the entirety of space is a pressurized system. It does not suck. The reason why your vacuum cleaner sucks is because there is a lower pressure inside the tube, right? And so the higher pressure on the outside wants to go in. That's why your vacuum sucks. So the thing is now,
you don't think temperature has anything to do with it?
No, not at all, because what is the pressure at sea level?
Why don't you go ahead and tell me?
It's 14.7, right?
Right.
Okay. So the pressure at sea level when you're standing at the ocean on the edge of Tanzania is 14.7 psi. When you're standing on the edge of Norway in the winter at 20 degrees below zero Fahrenheit, the pressure is 14.7 psi. The temperature is drastically different, but the pressure is the same. So it's definitely not temperature. Now, if you watch the video by Dwayne Kellum, I See Stars, video number 24, he has a barometer in there, and you can look at the barometer at when he launches it. He's also got a thermometer in there. Thermometer, right? And both of those you can see as it goes up in elevation. Now here's what happens. The temperature goes down and up, and the pressure just goes down. They don't match. It doesn't just it's not just a dropping temperature. So you can look at that video yourself to see that I'm not just making that up. I watched the video and I stopped it at different points and checked to see that the pressure and the temperature don't match. And in fact, U.S. Standard Atmosphere 1976 has a graph contrasting pressure with temperature, and you can see the pressure goes. It's actually an asymptote. It's not linear, and the temperature does this big old curvy thing. So there's that. What time? 9:14. So I have another thing at 10. That's 45 minutes from now. So just to keep in mind.
All right. This downward force, since we can't replicate this downward force on Earth, how do we know that that's what's keeping the gas in if there's no container? Because all of our experience here on Earth is that to have difference in pressure, you need a container containing it. You need a container and not have some sort of gradient.
What do they sometimes call a hurricane before it turns into a hurricane? They sometimes call it a tropical depression. Have you heard that?
Okay.
I think the reason why they call it a tropical depression is because the pressure in the middle of it is lower. So from the center of the tropical depression to the rest of the area is a pressure differential, and as that pressure differential gets greater, then it turns into a hurricane. And the greater that differential, the more aggressive the hurricane. There's no physical container from the center of that tropical depression or hurricane out to the rest of the atmosphere. So there's an example of a pressure differential without a physical container.
That's fascinating. Can we replicate that and create our own and test how different
you
molecules interact with it?
you could try, but we don't need to. We can observe these and we understand that. So you asked for an example where there's a pressure difference without a physical container. I gave that to you. If you want, you can also look at something like an airplane wing. The top of the airplane wing is a higher pressure than the bottom of the airplane wing, but there's no container, physical container between the top and bottom. There's the wing, but that's not what's containing that differential.
Right, but if this if the Earth is contained, then I mean that those are in a container. Those would be in a container, would they not? I mean, I fully admit that's a presumption on my end.
It's an absolute, yeah. You're absolutely presuming that. So yeah, sure. If everything is contained, then yes, everything is contained. And if everything is not contained, then everything is not contained. It gives us no information, right?
Well, that's why I was asking, can we replicate that and test it? You said we don't need to, but in order for me to remain intellectually honest with myself, yes, I do need to test that. I would like for anyone to test that.
So now you're being a little inconsistent.
How?
Because you think there's a container and you haven't tested it. You haven't seen it. You haven't touched it. You haven't gone to it. Yet you think that there's a container. You've not gone to the North Celestial Pole, and so then you doubt the existence of, or the elevation to it, right? But on the other hand, you think there's a container, but you've never been there. You don't know what it's made of. You haven't seen it. You haven't touched it. You haven't gone there with the tape measure to see how far it is away, right?
My experience.
It's inconsistent. No. You can't say my experience because you're talking about replicating it in a lab. So can you replicate the dome in a lab?
I would love to. Not at the moment. I can't.
Okay, nobody can. Right?
Well, right. Of course, I know that.
So, and here's the deal. Here's the real deal. If there is no mass accelerating mass force, right, or mass to mass attraction, then the second law of thermodynamics has a problem with the flat earth idea, right? Because if there is no force causing the pressure differential, then the second law of thermodynamics says that this pressure differential will equalize.
I'm sure there is a force. We can observe the effects of it, right? But what I disagree with is that it's gravity. I think it's something a little more electrical in nature.
Okay, but if it's electrical, then a Faraday cage would block it and you'd float in a Faraday cage.
That's assuming that we know that we understand all of the properties.
Well, we do.
Yeah.
We understand very well electricity. Right. You're talking on a computer right now.
That's quite a bold.
Yeah.
That's quite a bold.
It is bold.
Do you know everything about electricity? That's my thing.
Oh yeah. Well, so you want to. The problem is you're trying to substitute something that does work and has absolutely no known contradictions for something that you don't know anything about, can't describe, can't do anything. Just it's a rough, vague idea. Because I asked for the formulas and you don't have them. It was a rhetorical question. I know there are no formulas for it, right? You want to talk electrical, you'd use Coulomb's law, but Coulomb's law doesn't work because as soon as if I am right here grounded to the ground and this is touching me and it's grounded to the ground, yet it still has a force down, right? If it's grounded, Coulomb's law says that's not going to work. This is going to be the same electrical potential as the ground. It's not being accelerated to the ground. Right? So what do you have to replace to explain this force using the electrical universe?
Well, I was in the middle of looking that up.
Okay. I'll tell you what. You do that. I got a couple super chats while you do that. A couple things to say. So sound good? So ignore me for a second here. So we got Mark Beiser. Thank you very much. New Newton member. Mark and I met in Texas, and Mark even gave me a ride to our friend's house which was nowhere near where we were at the conference. So thank you very much for that, Mark. You went above and beyond for that. Stringer News 1 is a new member of Newton. Thank you very much, Stringer News 1. Bella Charge for $2 New Zealand dollars says we had a probe go out of the solar system. We did. V'ger. It's going to come back someday. V'ger. I hope it doesn't bring destruction. Now, Star Trek fans, so you know. Do you know the rule on the Star Trek movies? The odd number movies are not so good, and the even number movies are good, right? Oh my goodness. Clive Wells. I don't know what that is. But I do know what ketchup chips are, Punchy. I'll get to that in a second. We say, let's see. Lael is fun for $10. Says, fact, I can take a tape measure and measure it every 10 feet for 100 miles and drive 100 miles and check my odometer. Or I can just trust the odometer makers have accurately done measurements. Absolutely. And Lael is fun as saying that's the true distance to the North Pole. Yes, absolutely. We can use the odometer to measure the distance between a line and latitude and go from there. So Punchy says for $2 Canadian dollars, happy ketchup chip day, fellow Canadians. Look what I got. Oh, yeah. All right. Hey, James, do you like ketchup chips?
No.
No, neither do I. Punchy gave me these when he came down March 12th. Still crunchy. They taste different than they used to, being that they are March, April, May, June, 3 months old. Wow. And then, of course, it packs into my teeth, so I get to enjoy it the rest of the time. So there you go, Punchy. Just for you. Crafty Keela for €2 says, tune you are credit to sanity, and then a little heart. Thanks, Crafty Keela. I was at my sister's house for my nephew's graduation party, and they have goats, and I sent Crafty Keela a picture of the goat that I was petting. And then Sarcastic Barman for €2. Yes, we do McToon for Prez 2020. I would not want to be president. Holy crap. Ben Roberts. Surveyors triangulated the altitude of high mountain peaks, such as Mount Rainier in Washington, before anyone had climbed them. That's true. Ooh, wash it down with a delicious tab. There is no such thing, Extra J. There's no such thing as a delicious tab. It is not delicious. This one is unopened. I have 2 unopened ones. I don't know why. Probably because I don't want to drink them. We got some tabs in the chat. Okay, so
I'm finding stuff trying to explain dielectricity, but I'm not finding actual formulas. So
yeah. It was a rhetorical question. I know there is no explanation in the electric universe for the downward acceleration. People that don't understand electricity and stuff will say, "Oh, it's that works," but it doesn't. Some will say it's magnetism, which doesn't work either because lead is diamagnetic. So lead would float instead of being one of the heaviest things there are. So,
well, rubber is just rubber, but you can still it can still be affected by static electricity or static fields.
Yeah, but like I said, a Faraday cage would block that. So, so let's see. Okay. So now here's the thing, and you you said we should look at the things that are on the ground to measure the ground, which of course we can do, right? There's all sorts of ways. It's easy for us to measure the elevation of something in the sky because we can see it. We don't need precise instruments, right? You can install the Theodolite app on your phone to measure the elevation of the sky. Hold on a second. The guy that is coming in a few minutes here sent me a message. I just want to make sure that he knows that anyway, I got to answer his question. So come on. I'll send a link. Okay. So on my website at mctoon.net/r, we have measurements made by geodetic surveyors, or at the time, surveyors, that measured the elevation, or not the elevation, the shape of the Earth. So let's see here. So we've got I have 6 of them listed here. These are all older ones. They're all pre-satellites. They use satellites nowadays, but these are all pre-satellites. So Sir George Everest, who also measured the elevation of Mount Everest, it wasn't him. It was the people after he went home from India. Other people did that and then named it after him. But here's the one in 1990: transcontinental triangulation and the American arc of the parallel. Now that particular one, they measured from the east coast to the west coast, ocean to ocean. They started by measuring by getting their position exactly correct on the Earth using celestial navigation techniques, right? So the elevation of Polaris, the time offset from Greenwich Mean Time, the different. There's a bunch of stuff. It's pretty complicated. I don't know all of it, but they got the position of their starting point and ending point. Then they use a chain that they know the exact precise length of that chain, and they measure out a long distance of that chain. They get 2 points between that, and then from there they do triangulations. Every once in a while they verify by getting their latitude longitude again, and every once in a while they use that chain again to make sure that as they go they don't include and compound errors, right? So this is what we're looking at here. Oh, you're not seeing this, are you? You're probably not looking at the stream, are you?
Oh, I can. Hold on.
Okay, yeah. Just look at that. It's I mean, I can share it to you if you want, but this is just an example of one of the triangulation like collections of triangles that they did. So you can see like Colorado Springs, Pikes Peak, Big Springs, Dry Camp, Kramer Gulch, Square Bluffs, Adobe, Plateau, right? So these are different places that they triangulate to, and you can see there's lots of triangles that they put in there. And they measure all these triangles, right? And that's how they then they do the math to know then how far they are from one point of the country to the other. They do it across the 39th parallel. Now, on the surface of a flat surface, when you have a triangle, the sum of the internal angles add up to 180 degrees, right?
Yeah.
Okay. On the surface of a sphere, every triangle adds up to more than 180 degrees. It's just called a spherical triangle, and the amount of overage over 180 degrees is called the spherical excess. You can test this yourself. Take a string, put it on an exercise ball or a basketball or any anything that's a sphere, right?
Yeah, I remember doing this.
Yeah,
a couple times.
draw, draw a line across it, do another 2 points, get a triangle, then pull out your angulometer, which we also call what?
What?
Your an angulometer is also called a protractor. You get your protractor out and you measure those angles, right? And so rather than like 60, 60, 60 degrees, you might have 62 degrees, 70 degrees, and 81 degrees. And you add them up, you get more than 180 degrees. Every time on a sphere, you get that. So here's the cool thing. When measuring big triangles on the surface of the Earth, if they add up to 180 degrees, that's evidence that the Earth is flat. If they add up to more than 180 degrees, that's evidence that the Earth is a sphere. So here we go. This is one of the charts from the table, page 218. You can see here, Ibapa, I don't know how to pronounce that. The angle from Ibapa between Pilot Peak and Ogden Peak, right? So you're at Ibapa and you measure Pilot Peak over to Ogden Peak, 53 degrees, 38 minutes, 37.117 minutes. So that's, degrees, minutes, seconds. Then at Pilot Peak, they measured between the other two 91 degrees. At Ogden Peak, 35 degrees. You add them up and you get more than 180 degrees. In fact, you get 62 arc seconds more than 180 degrees for that particular triangle.
Where are these places?
So Pilot Peak, Ogden Peak, these are, they measured peak to peak because, I believe this is on the west. I think this is near the west. So it's in the Rockies, I believe. But this particular book, and I have it linked on my website, is full of these, just page after page after page of these measured triangles. Right. So what they'll do is they'll go up and they'll set. This was done in the late 1800s. No cars, no phones, no nothing. They'd set up a base camp at the top of a peak. They'd build a little structure there. They'd bring up their theodolites, very big theodolites, and then they'd say, okay, tonight we're going to measure between these two peaks. So for 2 or 3 or 4 days, the people at the other peaks would have a fire, and then they'd have things to shine the light towards the other peaks so that they could measure the angles between them. They do it over and over and over again and get a very tight margin of error on these measurements. The real nice thing about horizontal, I'll say this and then you can ask. Horizontal measurements are not affected by refraction like vertical measurements are. Vertical measurements can be very much off based on atmospheric conditions. Horizontal measurements are not affected in the same way. It's possible, but it's very rare, and you can find the outliers and get rid of the outliers. So go ahead.
These are, you said peak to peak, so at the height, absolute at the tips from or at the highest elevation of each, right?
Yeah.
Is that what I'm?
Yeah.
Okay. Would it be valuable to try this over water? Like what, or what's stopping this from being measuring differences in topography? Since it's over land, obviously lands are jagged. There's different elevations in topography and all that stuff.
So are you concerned because of the elevation differences?
No. I'm just trying to get as much results as I can.
Yeah. So these are horizontal measurements. So the vertical measurements aren't. So just because some people are concerned about that, thinking that because they're at higher elevation, it's adding things.
Yeah, I know.
But the deal is, if it were just because of elevation, then you'd have some that would go over and some that would go under based on your elevation shifts. But all of them are over. From the east coast to the west coast of the United States, every triangle is over 180 degrees. Right? And of course, there's huge amounts of land in here. You can see distance in meters, 185,000 meters. So this is 185 kilometers, 230 kilometers, 133 kilometers. This is a gigantic triangle. There's lakes inside them. So that it includes water. It goes over the rivers in between. It goes over any lakes, anything that's on the 39th parallel. And they don't just go right across it. They get a much wider swath so that they can get big triangles so that they can have accuracy. So now lower down on that page, I actually have a section called Spherical Excess. And in California, Washington, and Oregon in 1913, a different survey happened. They did the same thing. And I have 10 pages of, this is a smaller survey. It doesn't have hundreds of pages. It just has 10 in this particular one. 10 pages of the same thing. Oh, they're not zooming in here. I got to change how, oh, there it is. There we go. All right. So Tacoma North Base, Tacoma South Base, and rain. You can see here, spherical excess over on the right side, 0.58 arc seconds. So this is a small one. 2.33, right? So all of these, same thing. Every single triangle.
All of these were what went over 180.
Yep, that's what the spherical excess is here. This is how much over 180 it is. So this is hundreds of measured triangles using surveying techniques that all went over 180 degrees. So if the Earth were flat, they would all average out to 180 degrees. You'd have some over, some under because of errors, right? And there's always a margin of error, and they include a margin of error analysis on this. So there you go, Mount Helena.
I'm going to be completely honest. I need to talk to some surveyors and get.
Yeah. So there's
opinions and stuff.
Yep. So there's, in fact, if you want to, Jesse Kozlowski. Jesse Kozlowski is
in the chat.
Nope, he's not in the chat. He's a surveyor. He's a professional geodetic surveyor. And here is his measurement. This is a different one that he did. He measured to see if across a lake, if there was a drop. And he found that there was a drop. If you look at this, if you see in the live stream here, this is you can zoom in on your own. I'll send this to you as well. I'll actually send it to you in Discord because it's you'll have it because the chat, the live chat that we're using here, the side chat will go away. So anyway, you can see here that the crosshairs is slightly above the thing on the other side. So the thing on the other side is another theodolite that's got a target. It's specifically designed so you can target and get the vertical elevation across it. So so it dropped, and he went to the other side, and it dropped from the other side. And then he did, and I'm not going to go over all the details here. Oh yeah, you can see this is the little like target thing there. But I'll jump down to the bottom where he actually has his numbers. And there it is. So he has 1, 2, 3, 4, 5, 6 different measurements. And the distance is 0.48 miles, so just under half a mile. And the drop from horizontal was 0.15 feet. So all of them came out to be a 0.15 foot drop, and that matches the other times that we've measured the radius of the Earth. So there.
Does he I saw that he put out a few videos and presentations or something.
Yes.
Particularly before you clicked on it.
Yep. Yeah, he does videos. You can find his videos on YouTube. Another surveyor by the name of Jeff, the Main Surveyor.
Mm-hmm.
So I'll just, let's see. And Main Surveyor is in Maine, and he has done the same thing. He's actually done what's called reciprocal zenith angles, where you point two theodolites at each other, similar to that lake thing, but you don't have to do it over a lake. You can do it anywhere, right? And you know where you're at. You don't need to know where they're at, but you need to know how far they are from each other. And then even if they're at different elevations, what you do is you sum the angles, and if the angles add up to 180 degrees, then you're over a flat surface. And if they add up to more than 180 degrees, then you're on a curved surface. So there, I sent you those two things.
Yeah, I got them.
So I've talked to both of them a couple times.
People?
Oh yeah. Okay. Actually, if you want to see, if you know Jose J.G. Gonzalez, he has a YouTube channel, and he does lots of debates. But on Saturday, he had Jesse Kozlowski on his channel to give a presentation. I haven't yet watched it, but Jesse does excellent work, so I'm sure it's pretty good. So I've given you a lot of evidence, a ton of evidence, and you've given me some globe evidence too. So we've got just over 15 minutes before the next one here. Do you have any other questions? And maybe the chat will have a couple questions. Tag me if you have a couple questions for him.
I do. I would love to get together and have some chats with some people like this.
Yeah.
Maybe not broadcasted, so it would be more of like an instructional type, educational type thing instead of like publicized debate type atmosphere.
Yeah.
'Cause I would love to learn about it, but it's hard to really learn in this type of atmosphere because it feels like it's like a you versus me type thing.
It does, and I don't, it's hard to avoid that,
Yeah, that's why I was when you approached me, I told you I would love it to be a little more of a back and forth type thing instead of a debate, because it's hard for me to learn this stuff if it's always like, all right, what do you got? This is what I've got.
Yeah.
What do you got? Like,
so well,
instead of I can't learn that.
Yeah. So here's what I'll give you. Feel free to message me, and I'll talk to you all you want, right, on Discord. If you want, you can join my Discord server. It's I'll send you an invite to it. It's a much quieter server than like FTFE's server.
Yeah.
So you could and so you can have a pretty decent conversation in there, I think, with some of the people in there. So feel free to do that if you have questions, if you think something doesn't make sense. But you're open at least, and I think you're willing to look at things. So I think that that's the important thing, right?
Yeah, of course. See, when people think that they get things, it's hard for me to even really converse with them, because they're just gonna be so matter of factly about everything. If you stay humble and understand that, like you even said earlier, science is always open to new things. There's always that open door of, hey, something may be wrong. Let's go look at it real quick. That's what I'm trying to do. I can't just accept everything. And when people just, I don't know, I can't just take everything because someone says it, or I think I missed where I was going with that at first. I'm sorry about that.
That's okay. Let's see. Let's see. Andreas Eld says, "Give him your White Swan's modus tollens as homework." I did a video with 5 different modus tollens. So how about this? Have you ever watched the 200 proofs from Eric Dubay?
Yeah.
Okay.
It's been a while, but I've watched it a few times.
His claim number 2 is that the horizon the horizon always rises to eye level. That's his claim.
Yeah, right? Even flat earthers have picked apart a number of those.
Yeah. So here's the deal.
So yeah, I'm sure there's a flaw in that.
That came from Samuel Rowbotham, who made that claim, and Samuel knew the math. It's pretty simple math. If the Earth is flat, then the horizon is very, very far away, and the angular difference between true level, or eye level as it's often said, and the horizon at that distance is essentially 0. If the Earth is a sphere, then the horizon must dip as you go up in elevation, right? So Samuel Rowbotham went in Brighton, UK, to the top of the tallest hotel there, which is I don't know, the Brighton Hotel. It's no more than 10 stories. And in his claim number 15, his Rowbotham's proof number 15, he said the horizon must drop at some large amount. He didn't do the math, because I think Rowbotham knew that. I don't think Rowbotham thought the Earth was flat. He made money on it, and that was his deal. So he didn't do the math, so it's not a very good experiment or a very good test. And then he didn't bring a precision instrument up there. He brought a tube with a string across it, and he called it an inclinometer. But from that elevation, the dip of the horizon is very, very small. You need a very precise instrument to test it. So here's the deal. Watch different claims about that, because it's true. The horizon must dip if the Earth is a sphere, and it must stay at essentially eye level if the Earth is flat. See if you can find any measurements from flat earthers, right? You'll see pictures and they're like, oh, look, it rose to eye level. But there's no measurements in that. You don't know where eye level is when looking out an airplane, right? There is a theodolite app you can put on your phone. I did put on my phone, and I took a picture out of an airplane of the true level and where the horizon is. And, well, there's your homework. Look it up. See if you can find any measurements at elevation of the horizon actually rising to eye level. So that's a request from Andreas Eld. Somebody else asked, what would it take? What would be convincing to you?
Oof. Well, if I could see the curvature with my eyes, that would be amazing. Though even Neil deGrasse Tyson says you have to go well above 23, 24, or even 26 miles.
I don't agree with what he said. I think he was just talking off the cuff.
He might have.
So there is a, and last I heard, maybe they're out of business, but there's a company in Florida that flies MiGs, and if you don't see the curvature of the Earth, they'll refund your money. It's very expensive, but people have done it, and so the guy from Top Gear did it. In fact, I forget his name. Chad, help me out. What's the name of the guy that from Top Gear that went up? So there's a video of him saying, going up, and he's like, I can see the curve. So
what was the windows of the plane made of?
Yeah.
The reason I ask that is because
that's the common claim. But all you need to do is look at the something straight when you're on the ground, and it's straight when you're on the ground.
I mean,
James May, yeah. So anyway, so a few different things went by. GPS. I don't know why they would say that. Hold on, let's get off here. GPS for $2 says MC for benevolent dictator. Hi, Gleam. So Gleam is on here in a week. Gleam and The Plain Truth and Conspiracy Cats and myself, and moderated by AT2 Productions. We're going to have a epic debate. It's going to be at 4 p.m. Central Time. So
I would love to talk to Conspiracy Cats at some point.
Yeah. Well, make sure you come next week. It'll be 4 Central Time, which I think on the East Coast is 5 o'clock, right? So you can watch that. So, all right. Well, there you go, people. If you're in my Discord server and you see the Mad Philosopher in there, help him out and give him any information that he asks for, right?
Yeah, I'm never gonna just deny evidence without looking at it. Of course, if I look at it and it's convincing, then sure, I'll admit it. But if I find that, I guess maybe reasonable doubt or something that I might want to look into further, I'm going to tell you, and I would ask that you don't just shut me down because I wish to look at something further. Just because I don't agree to it right away doesn't mean that that doesn't have value. It could have value. I just need to look at it further.
Yep. And do you know who Seek Truth, Speak Truth is? Have you heard of him?
I might have heard that name.
Okay.
Tossed around. I can't recall at the moment.
He's another good person to talk to. Can probably give you some good information. Has a good perspective on your position. So, Scythe DK show photos of the curved horizon. So let me. We do have a couple minutes. I'll show you this. On my website, mc2.net/curve. Anybody can go there. I have, let's see, the left to right curve of the horizon. So let me pull it up here on the live stream. So a guy named Rory went up to, this is where he went. He's in Ibiza. And he's about 600 feet above sea level, which Ibiza's an island in the Mediterranean. Mm. Right. So there's a setup that he brought these levels or straight edges up. And here he set it up so that his camera took a picture of the horizon between the two straight edges. Right. Okay. And so now you can zoom in and look, and I'll do that quick here. It's always difficult when you're zooming in because you can only see a certain amount, but here we go. We can scroll. Now, are you looking at this on the live stream?
Yeah,
okay.
I'm watching.
So you can see here it's down near a little below middle, right? And then you scroll to the right, it starts to come up, you keep going, and it starts to curve back down. That's hard to see. So if you compress it left to right, you see it.
Oh, I saw what you're talking about.
Yeah, you see it much more clearly when you compress it left to right.
That looks like it would be a wave. That doesn't exactly look like a...
So that would be a many mile long wave because that was a very smooth day, very calm day. And because we have the straight edge here, we know, because the straight edge we know is straight, and the camera cannot cheat by being distorted because the straight edge is straight. And so if we see the straight edge straight on the screen here, then we know that it is straight and that the thing behind it there is what's curved. Now there's another one that was from Ibiza, then another one from Norway, and this was at much lower elevation. And here's the picture. It's taken with a much higher resolution camera. And same thing here. I actually, rather than compress it, what I did is I went in and I counted the pixels manually in Photoshop. Here's what it looks like. I actually put a dot back and forth for each 10 pixels and pasted them back and forth so I could count how many pixels from the straight edge to the horizon. You can see here it's 32, 33, 34, 35, right? So this is zoomed in. So well, on the other side of 33 is less than 33.
Yeah, I know.
Right?
I'm just
so And so I
Talking
put that
shit.
into a spreadsheet and graphed it and did a line fit, and it's curved. It is a curved line fit right there. Let's see. Get the zoom right. So, and actually, it gives us the equation for it. So this is, negative 0.011x squared. So the fact that it's x squared means that it's not a straight line. So that is the amount of curve in that graphed out. So there you go. There's two measurements of curve. So this here is shows the fact that the horizon is curved because it's been measured. So there you go. mc2.net/curve. So people ask for that. We've got just a couple minutes left. So anything you want to say? Anything you want to add?
Well, I guess anyone that sees me asking around and poking around, I saw this in the chat a few times. I'm not denying everything that you present or everything that I hear or see. I simply need to look into it further and verify it. And I'm sorry if that offends some of you. That's on you if you're offended. I'm sorry about it, but it's just my my life choice to want to verify these things. And you can either help me by educating me if you have answers, or honestly just get out of my way.
All right. Well, good. I think that's fair. So I've got coming up in just a minute here. If somebody wants to grab the link and pop it in, a discussion. It's going to not be a debate. It's going to be a discussion with Keith, who thinks that 5G is causing a certain Mexican beer virus. So make sure you stick around for that. Let's see. I'll grab it here in case, so we don't miss it. Oh, there we go. Punchy put it in there. Thank you very much, Punchy. So there you go. If you like this, click the thumbs up. If you're not a subscriber, feel free to do that and click the bell. If you want to talk with the Mad Philosopher, come on my Discord server, and which the link is in the description, and let's have a chat and see what we can figure out. So thanks for joining, James.
No problem, brother. Thanks for having me.
All right. We'll see ya.